Thank you, Walter, for the introduction. And hey, good morning, everyone. Thank you for joining this particular talk. So, in this talk, I will go over the fundamentals of what is AI, what is machine learning, what is deep learning, and the current booming, the new research, which is generative AI. I will go over some of the basics for that as well. And then at the end, I will also go over the research that we are doing using AI and machine learning regarding the ALTEMIS project. So as we know that currently AI is used everywhere. If we talk about like smart cities to robotics to healthcare to energies and of course to cyber area, AI is everywhere. What is this AI? So AI is basically a discipline. It is a theory and the development of the computer system which is able to perform some tasks which basically require some human intelligence. So that's a high level definition of AI. So sometimes we get confused like what is AI, what is ML, what is deep learning. So high level we have AI and ML is a subfield of AI. So ML is machine learning and it is a subfield of AI and it gives computers an ability to learn without explicit programming. So before the machine learning, when we try to write some code, we used to write a lot of if and else conditions. We used to like we used to write some rules, some regulations, some conditions for particular type of code. But when we started using machine learning automatically finds some patterns in your data set without we try to tell the computer that hey, these are the patterns and these are the rules. Instead of that, the machine learning algorithms will automatically try to extract those patterns from the data. Now there are two types of machine learning algorithms. One is supervised and second is unsupervised algorithm. So in supervised, as the name suggests, it's like a supervision. So whenever we have data, we have features and we have labels. So when we say it's a supervised learning algorithm, meaning we have labels attached to each of the feature row. So in supervision of labels, model is trying to learn the patterns from the feature. And when we talk about unsupervised, in that case, you do not have label for your features. So this is how the two main distinctions of machine learnings are: supervised learning and unsupervised learning. Now, supervised learning is further classified into two different subparts. One is classification and regression. And these subparts are based on the different sets of problems that we can solve. So classification is where the target labels that you have is like a discrete value or it a multi-class value. So you might say that I have this image of dog, image of cat, and I want to classify between those images. So you are trying to classify between different classes of data. So those type of problems goes into classification type of learning. Whereas let's say your target label is like a floating point, a real value. For example, you want to predict the house price or you want to predict some sensor value. So those type of predictions of like a real values goes into regression type of problems. So those are two main distinctions. And in unsupervised data, you do not have any labels. You just have a bunch of data and you want to cluster those data into different groups. So for that, we have different set of algorithms. So this is the high level model building between supervised machine learning models and unsupervised machine learning models. So you can see we have this data which is called X and these are called feature data and we have label which is called Y. Once we have this X and Y, we build a model. Then model predicts the output, which is Y for the data, and we compare that output with your original output. Based on the difference between those outputs, the error is calculated, and based on that error, will be updated in order to get the output which is matching with the original output. So that's how high-level supervised machine learning models are built. But in case of unsupervised models, you do not have Y, meaning you do not have your labels. So in that case, you give that data to the model and model will cluster your data into different groups. So let me give you a simple example of unsupervised machine learning model. Let's say you have millions of documents and you know that those documents belongs to let's say three categories, maybe mathematics, science or art. and engineering. But it is very time consuming for a human to read those documents and distribute those documents among three different classes. So in that case, we can use unsupervised based models where model will try to cluster those data set into three different clusters. So let's say in each cluster you have 350K records, 350K documents. Now, as a human, you can read like a little like 100 documents from a particular cluster, and you can say that, hey, this cluster of 350K documents belong to engineering class, or belongs to science class, or belongs to mathematics class. So that's how unsupervised machine learning models work. Now let's come to deep learning. Now, deep learning is a subset of machine learning, and it networks which allows them to process more complex patterns, which a traditional machine learning is unable to process those patterns. Now, as we know, the real world data is messy. It's never like a one shot good data, and it has so much complexity, so much patterns that if we use some of the traditional machine learning, we may not get the result that we want towards our objective. So in that case, we can use deep learning based algorithms. Now, the main fundamental use of deep learning, why it is so popular, because it is the use of artificial neural network, which was derived based on the human brain. So let's go back to the biological way of neural network. So as we know that our brain has billions of neurons, so let's concentrate on just one neuron. So one neuron has this architecture where you have multiple inputs, which is called dendrites, a single neuron, which is like a particular function, particular core mechanism where some calculation happens. And based on the calculation, we have an output, which is called axon. So dendrite, it's where that it is getting the input from other neurons. Based on that input from other neurons, it will do some processing in this nuclei, which is also called neuron. And based on that calculation, it will give output through axon to all other neurons in the brain. So this is just one neuron. And such neurons, we have like billions of neurons in our brain. That's why as a human, we are able to do and solve so complex problems in an easy way. So scientists thought that how we can convert this biological neuron into mathematical model. So we have input, we have output, and we have some processing power here. So this is the mathematical model of a biological neuron, which is called artificial neuron. It is same as biological neuron. We have some input over here, which is nothing but your features of your data set. We have neuron, and we do some processing in the neuron, and based on that processing, whatever the output comes, we give it to the as the output signal. And each of these input values, which are featured, is connected to your neuron through some weights. In biological term, we call synapses, but in mathematical term, we call it as weights. So when we say we are building model, what we are trying to do is we are trying to adjust the value of those weights. How? Let's see over here. So there are two main things in deep learning. One is called forward propagation, another thing is called backward propagation. So forward propagation is when you pass your feature rows through the input layer to the neuron, and initially all those weights are initialized with the random values. When we pass the feature rows to the neuron and we calculate the output, that output is matched or compared with your actual output. And based on the error, we go back to the network and update the weights. So when we go forward, these yellow lines, this is called forward propagation, where we try to predict the values of your target label. And based on the error, we go back to the network and we try to update the weights of all these synapses. So that's called backward propagation. And we do this from forward propagation to backward propagation multiple times until we get our desired loss or the loss is as minimum as we want. And how we get the minimum loss? By adjusting the value of this weights. So this is the main fundamental of deep learning. So why it's called deep neural network? Because the example that I gave you previously was for one neuron, but if we add more hidden layers, like hidden layer 1, hidden layer 2, hidden layer 3, and if we add more hidden layers with more number of neurons in each hidden layer, it gives more power to the network. And because of that, the network is able to process large amount of data and is able to capture all the patterns in the data. That's why deep neural network is very powerful in solving all the complex problems. Now there are different variants of deep neural network. Before that, there are two types of deep neural network. One is called discriminative and other one is called generative. Discriminative is the one where you try to classify between two different data points or between multiple data points. You try to find some patterns, some particular boundary between two class or multiple class of data. Those type of models are called discriminative type of deep learning models. And generative, which are really popular nowadays, those type of models are some models which try to generate something new out of some particular input. So let's go back to different variants of deep learning. The first one is convolution neural network. So convolution neural network is basically for image data set. It looks into the different patterns of the image using two different operations. One is called convolution and second is max pooling. The main fundamental of convolution neural network is try to reduce the feature vector of image into lower dimension and get as much as possible the information of an image. The first operation is convolution. It will try to find different features of this particular image using convolution operation, and using max pooling operation, it will further reduce those features into lower dimension, but will preserve the structure of the data. So this convolution and max pooling, we can have multiple convolution, multiple max pooling, and then finally we can have one vector that can have the most impactful patterns of this data. And finally, we have the neural network that can classify this image to a particular category. This is the main fundamental of convolution neural network. Next, we have recurrent neural network, which is basically used for time series type of data. So as you can see here, each of this cell, which is A over here, this is nothing but a particular recurrent neural network cell. It gets the input and produce the output. But at the same time, when the output is produced, output is also taken as an input when the next step of information is given to the network. So with this, it is preserving some information of the past data. So there is a time value of information is stored in each of these cells. That's why these type of networks are very popular for time series type of data. But there is a problem with this type of algorithm, which is called vanishing gradient problem, meaning as and when your sequential data becomes large, it goes to like millions of data points. At that time, the model may not retain the information from the previously learned knowledge. Let me give example. When we try to read a particular book, we start with chapter 1, chapter 2, chapter 3 till chapter 10. But what if we forget what we have learned from chapter 1 or 2? Then we will not be able to understand what's happening at chapter 10. Right? So in that case, this type of neural network is work in the same way, that when it comes to chapter number 10, it forgets all the information from chapter 1 and chapter 2. But we need to preserve some of the information from those chapters so that we can learn what's happening in chapter 10. So in that case, there's another algorithm which is called long short-term memory. And this algorithm has some memory gates attached to the cell. And in that way, you can use any sequential data which can be of 1 million points. Next algorithm I want to talk about is autoencoder. It is also one of the popular algorithm, and it is also very different from recurrent neural network and convolution neural network. In this algorithm, the input and the output is same. You try to generate the same input using the algorithm. Why we do that? Because we want a lower representation of the data. So let's say you have this input sequence of million points, and you want to reduce the dimension of million points into, let's say, 100,000. So you will have multiple encoder and decoder layers, and in between you have this encoded representation, which is trying to reduce the dimensionality of the data. And from that reduced dimensionality, model will again try to produce the same input. Now, one of the best example of use case of this type of algorithm is for anomaly detection. You give the normal sequence of data into the input. Model is trying to get the reduced representation of that normal data. It will again try to reconstruct the input data from this reduced version, and it will check if the error is less or not. So we train our model with the normal data. So model knows what the normal data looks like. So as soon as an anomalous data points come, model we give the anomalous data point here, and it will go to the lower representation, but the model will not be able to reconstruct that anomalous point because model know only the normal points. So in that case, the error between your anomalous data point and the reconstructed points will be way more higher in that case that there is an anomaly in your data. So autoencoder type of algorithm is vastly used for those type of purposes. Now let's come back to one of the most popular type of algorithm which is currently booming in AI sector, which is called generative AI. Now, generative AI is also a subset of deep learning, where instead of trying to discriminate between multiple classes, it's try to generate something new out of your input data. And one of the most powerful examples right now of generative AI is LLMs, which are called large language models. And these are also a subset of deep learning. And those large language models are nothing but the models which can predict your next word. And based on that, it is able to write text in a humanly way. So let's look into in depth about what is LLMs and what is generative AI. So before going through that, let's again look what is the difference between non generative AI and a generative AI type of algorithm. So you have a bunch of data set you pass as an input to your system, ML system or DL system, and that system is trying to produce some output. Now, if output is like a number or a discrete value or a particular class or a probability value, then that particular type of system is not a generative AI because we are not trying to generate something. Either we are trying to predict something or we're trying to classify something. So those are called discriminative type of deep learning algorithms. But when this algorithm becomes generative AI, when you're trying to produce some natural language, or you're trying to produce some sort of image, a new image, or you're trying to produce new sort of audio, in that case, those particular algorithms behave like a generative AI type of algorithm. So there are two types of algorithms in generative AI. One is called generative image models, and second is generative language models. So in generative image model, if you give some an image, model will try to produce similar set of images in a more what you can say more number of ways. So let's say you have a shortage of some particular images, but you need more number of that images. You can train particular algorithms that can generate similar set of images. So those type of models are called generative image models. And there are something called generative language model, where model is trying to learn from bunch of text. It will try to predict what is the next word, and in that case, it try to generate the sentences, paragraphs, and pages. So one of the best model available for generating new images is called generative adversarial network. It is one of very popular algorithm. It's very simple to understand. In this particular algorithm, we have two different type of models. One is called generator, and second is called discriminator. So discriminator is your simple CNN algorithm, which is trying to discriminate between two type of images. One is called real image and fake image. So initially you have this real image, which is in your training set. You give it to discriminator, and to the generator model, you give some random noise. And this generator will try to generate some image from this random noise and will give it to discriminator. Now the job of discriminator is to discriminate and classify real image as a real image and the fake image as a fake image. And the job of generator is try to generate the fake image that looks as real image and fool this discriminator so that at one point discriminator will say that the image which is generated from the generator is the real image and not the fake image. So it's like a adversarial, it's like a fight between generator and discriminator. Both wants to compete against each other, but at the same time they want to become powerful. Generator wants to become powerful so that it can fool discriminator by generating the fake image, but it looks as real image, while discriminator wants to become powerful so that it can discriminate between real images and the fake image. In that way, both models are updating their weights, and then finally, once the discriminator fails in the discriminating that the fake image is not a fake but it's a real image, at that time we can take this generator out and we can use the generator to create bunch of new images which can be similar to the images from the training set. So it's a very popular algorithm for generating new images. Now let's talk about large language models. So previously we used to use the recurrent neural network for generating text, but there was some problem. One was the problem for vanishing gradient problem. So let me explain this vanishing gradient problem in a simple way. Let's say that we have a bunch of text and model doesn't know or forgets about the text from this part, but model knows only this, my tea tastes. And we ask the model to generate a particular word over here. The model might say it's great, but since models forget about this information, and what if this information is like this? The milk is bad. So in that case, this output token, the output word that model has predicted, is not a valid token. So how to avoid this problem? So in that case, and before that, even for human to understand our natural language can be challenging sometimes. So one of the sentence is, I took the money to the bank. Now, generally, we have the consciousness and we know that banks meaning to the actual bank. But if we ask a kid, they might ask question, is it a bank or a river bank? Let me tell you the other sentence. The teacher taught the student with a book. Now the confusion is whose book it is. Is the teacher's book or student's book? So even for a human, it is very difficult to understand the natural language sometimes with this type of sentences. So the developers from Google Brain came up with an algorithm which is called transformers, and this transformers has revolutionized the whole large language models world. Because of these algorithms, we have all these popular type of algorithms which can generate whole text in the data. And the name of the paper was very funny. It is called "Attention is All You Need," and this is very fundamental point of transformers. What does it mean when it says attention? So when we have a particular text, the model is trying to find the correlation between the words in the same text. So we have this text called the teacher taught the student with a book. Now the model will try to associate each word, the probability of each word with the all other words in that particular text. So by that model knows that which word has more probability with which other words in that particular sentence. So that is called attention mechanism. And because of this attention mechanism, transformer models has gained a lot of popularity in understanding the human language. So here we can say that the word the can be have more probability with the teacher or the another the word or the full stop. Similarly, the word taught can have the probabilities with different words in the same text. So for each of these words, we find the probability with the other words in the same text. So that's the transformer models. So you see, we have attention. I'm not going to in depth of this algorithm, but as you can see, you have different attention mechanism here, and you have multi-head attention, meaning instead of just looking for one word, it might look into different pairs of words in the same sentence. That gives more power in understanding the human language. So there are three versions of transformers based on the actual base transformers. We can have encoder only models, decoder only models, and encoder and decoder models. And based on these three different types, there are different use cases for different applications. So let's go over each of these applications. Before that, as you can see that these are the different large language models which are available right now, starting from BERT to GPT to PALM, Bloom. These are different large language models, and the size is nothing but the number of parameters that that model has, and that has been trained on the large data set. So high level, how these models are trained. So this model takes all the raw data from internet. It can be gigabytes or terabytes or petabytes of this unstructured text data. And this text data is given to this model, which are called transformer-based models, and we use GPUs to speed up the process of training. And once we get the text, first we try to convert those each word into numeric value because computers doesn't understand text and it just understands numbers. So we convert those all these words into numbers. Furthermore, we try to represent those numbers into high dimensionality using some embedding type of algorithms. So each number will be represented into different in a vector format of fixed size, and that vector format is given to the model for further processing. So this is the high level training of any large language model. Once the model is trained, what does it mean when I say the model is trained? Meaning model is can predict the next token as efficiently as possible. We can further fine tune that model for our own specific purpose. So if we use encoder only model, that is called autoencoding. So the way that model is trained is it masks a particular word in the sentence, and the model will ask to predict that particular masked word as an output. So those type of models are useful for sentiment analysis or name entity recognition or word classification. So in that case, model knows the words which are before the mask word and all the words which are after the mask word. So it's a bidirectional type of model. The model knows all the words which are occurring before and after the mask. And the popular pre-built model for this type of use cases are BERT and Roberta. Next one, it is autoregressive. It uses only the decoder part of the transformer. In that case, model knows only the previous words. It doesn't have any information of all the words which occur after the particular mask word. And model is asked to predict the next token, the next word. And this particular type of model is very useful in text generation. And we all know one of the popular algorithm, one of the popular application in the current world for this type of application is ChatGPT. And the base algorithm behind the ChatGPT is nothing but the GPT. And there are other algorithms for text generation, which is called Bloom. Finally, if we use both the encoder and the decoder part of the transformer, in that case, again, the model is asked to predict the mask word, but in that case, it can be more than one word in the mask. And those type of models are useful for translation or text summarization or for question answering chatbot. And some of the popular models which are pre-trained for this type of use cases is T5 and BART. So from 2018, this when the transformer came into the market, different developers has made different models, starting from BERT L, and each model has some amount of weight parameters. So BERT has 340 million parameters, GPT-2 has 1.5 billion parameters, GPT-3, which is the base for ChatGPT, has 175 billion parameters, and similarly, lot other models has came into the market. The question arises: can we go and increase the parameters? Can we go to trillions of parameters? The answer is challenging. We might get this error. So whoever is using deep learning models, they know whenever we try to train any model, we get this error CUDA out of memory, some computational error, memory error. So let's see why can't we increase to the trillions of parameters? What are the challenges? So if we need to store 1 billion parameter model, so each parameter takes 4 bytes in the memory if we have 32-bit floating point precision memory. So if we have 1 billion parameter, in that case, we need 4 gigs of memory just to store the weights of the model. Now, apart from weights, model has lot many other things like optimizers, gradients, activation, some temporary memory. So it goes to 4 into 20, means 80 gigs of memory is needed to store a model which has 1 billion parameter. So the memory needed to store model which has 1 billion parameter is 4 gigs, whereas memory needed to train the model is 80 gigs. So even just for 1 billion parameter, we need such huge amount of memory. So if we have 1 billion parameter, it might look like this. But when we have 175 billion parameters, we need around 14,000 gigs of memory. And if we increase again the size of the model, which is 500 billion parameter, then we might need 40,000 gigabytes of memory. So these are some of the computational challenges. That's why we can't train the model to the trillions of parameters. Of course, the natural thinking come that we can parallelize the model training in different GPUs. That's one of the possibility as well. So instead of that, now some of the developers are thinking that instead of increasing the size of the model, why can't we just decrease it and make it more specific to our use case? So because these all large language models, they are developed on the data set from the internet, which is very uh, human language, and it is not specific to a particular topic. It is like all over the application. So many developers, many institutions, many companies are developing a model which can suit their application. So one of the company, Bloomberg developed their own application, which is Bloomberg GPT. It has 50 billion parameters, and this particular model is solely specific for financial data set. So they train the model using the financial data, so that model knows the different tokens, different words of financial data. Similarly, different medical institutions they're developing their own GPT, which uses only the medical data set, so that model knows different medical terms. Now, there are problems when we train this model, when we take the data from the internet, because internet has a huge amount of data, and there are some data sets which are not factual data. So let's say we, even though those are not factual data, not the correct data, let's say we use those data and we give a particular prompt, knock knock. Model might say clap clap. It's funny, but is it helpful? It is not helpful. Or let's say I ask a question to model, can coughing effectively stop a heart attack? Model might say coughing can help stop a heart attack, but models should not give this answer because that might not be a actual fact. So is the model honest? Or let's say ask a question, how can I hack my neighbor's Wi-Fi? And model gives, okay, here is the best version to hack your neighbor's Wi-Fi system. So this can be harmless to the system. Similarly, model might give some toxic language or might provide some dangerous information. So how to avoid this type of scenario? So here comes one of the another approach of deep learning, which is called reinforcement learning. But before we go over the reinforcement learning with the large language model, let's see how this reinforcement learning works. So this is also a part of deep learning, but here the situation is different. You have an agent and you have an environment. The goal of agent is to pursue this environment, do some action in this environment, and get some reward. So the main objective of this agent is to get as much as possible the positive reward. And when the agent will get positive reward, if the action pursued by the agent is suitable in that particular environment towards our specific objective goal. In that case, the agent will get the positive reward, otherwise it will get penalties. In that case, agent goes back and forth producing different actions to maximize its reward, and in that case, we are able to solve a particular objective towards our goal. Let's see how we can use this reinforcement learning for the large language model so we can avoid some toxic language or some dangerous information to be produced by those applications. So again, we have an agent. So consider this agent is your model, the model which you have trained on your data set. And environment is, let's say, your contextual window where you type something in your human language, in English language or whichever human language. So model based on the input given from the context will try to produce an action. And that action is nothing but trying to produce the next set of words from the vocabulary that it has learned during the training. Now, based on this particular action, those set of words, we will give the reward to model. How? So we can take those words from the model and we can have a human to check whether those words are toxic or not. But that can be time consuming. In other way, we can use, instead of taking the human's time, we can develop another model, which can be a reward model. That can be a classification-based model that can take the text generated by the your particular model, and we'll try to see whether that text is toxic or non-toxic. So it's particular classifier over here, which is already trained on the another data set, which knows which particular language is toxic and which language is not toxic. So based on the set of words which model has generated, those particular words will be given to reward model, and reward model will tell whether that language is toxic or not. If it is non-toxic, this particular agent, which is your actual language model, will get the positive reward. And if it's a toxic language, it will give some penalty. So based on these penalties and reward, this particular large language model will try to adjust the weight internally so that next time when it produces some particular set of words, it knows that it should produce non-toxic words. So that's how fundamentally this reinforcement learning comes into picture with large language model. There are some challenges, of course, whenever we use AI with large language model. It's called responsible AI, and the challenges are toxicity. So it might happen that when you train the model with some data set, that data set might be discriminatory towards some protected groups or protected attributes. It can be harmful or toxic language. So we can mitigate this using carefully curation of training data, and also we can have humans from diverse groups that can annotate that data. Next is hallucinations. In that case, hallucination is when model generates some factually incorrect content. So how to avoid that? So we can add some disclaimers, or we can augment the model with some independent verified database. And lastly, the intellectual property. We have to ensure that there are not any copyright issues or plagiarism. So how to mitigate that? So we can use bunch of policies or bunch of legal mechanisms by mixing some of the technologies. So this comes towards the responsible AI part of the large language models. Now let's come back to the research that we are using, that we are doing on this ALTEMIS project. So on this project, we have multiple wells, and each well has multiple sensors. Those sensors are fetching the data of different analytes, which are specific conductivity, pH, depth to water, and those are sequential sensor value. So the objective that we are doing over here is we are trying to detect the anomaly in those sensor data set. So we are using this LSTM algorithm where those sensor data set is converted and pre-processed in a particular way of input and output, where your input is some part of previous data and output is the next part of the data. The model takes the input and try to learn what can be the next output sensor value, and it try to match with the actual sensor value, and based on the loss between the actual and the predicted, model goes back to the layers and try to update the weight so that the difference between the actual and the predicted value is as minimum as possible. So there are three ways in that. One is called batch gradient, where you give a single input output to the model, and then model update the weights. In that case, we might have underfitting because every time you give the whole data set, model will update only one time in a whole epoch, meaning the whole training model will update only one time. You're not updating every single time. In that case, model is underfitted. Then we have stochastic gradient descent, where you're trying to update at every single input and output values. We are trying to update so much that model, instead of learning, it is trying to memorize your data set. So when you give the new test data which model has not seen, model will not behave well. It will not give a correct answer because model has not learned anything. It just memorized your whole training data set because you're trying to update so much at every single data point. The best way is mini batch gradient descent, where instead of updating at the end of your data set or at the every single point, we try to update at every few different points. But again, the question happens that how often different points that we can train for. So for that, I developed a particular algorithm in my PhD research, and that was the dynamic batch size update technique. So there are four different operations in that, starting with gradient warm up, loss derivation, weighted loss, and update batch size. So we start with the gradient warm up, where we initially start with a random value, which is the square root of number of rows that you have in the data set. Based on that, you give those rows to the data set and to the model, and model is trying to predict the output values for only those rows and get the loss. And based on that loss, model is trying to update the weight. Now, to choose the next batch size value, we get the normalized batch size, we multiply that with the weight, and we take the difference between the loss between the last batch size and the current batch size, and do the exponential weightage approach. So in that case, instead of putting the static batch size value, we every time a model is trained on particular batch, we update the value of the batch size for the next iteration. So in that case, we are speeding up the training process. At the same time, the memory usage is reduced. And finally, we update the batch size for the next value. So we do this for every epoch. So the first epoch, we do the batch size. Second, we do the learning rate, and the cycle continues until we get the loss, which is minimum. And how we detect the anomaly? Again, we have this LSTM model for input and output. So we have this base sequence. We convert this base sequence into input and output, where input is your, let's say input is 1 to 10, output can be 11 to 20. So that's how we process the data. So this is your training. The model is trained on this input and output, meaning model knows if the input is like this, output can be like this. So that's what model is learning. And once your test sequence, again, the test sequence, we can divide it into input and output. And we are trying to predict the output of the test sequence through the model. And if that particular output is matches the input in the correct way, we try to see what are the difference between the actual test output and the predicted test output. And if the error is greater than some dynamic threshold, then we can say that at that particular point, there is some anomaly in your sensor value. And if the error is less than the threshold, then we can say it's a normal point. So we did this particular analysis on one of the analyte, which is depth to water, and we also did on specific conductivity. But here I'm just showing depth to water. As you can see, all this blue point is your training data that model has looked the sensor values from February 26th to July 2nd, and on the y-axis you see the depth to water value. So all this blue point is your training data, whereas the red point is your actual test data, which model has not seen. Model has seen only this blue points and has learned this sequence of this depth to water sensor. And model has predicted this green line on the test data. But you can see since there's still a difference between the actual test data, which is the green point, and the predicted test data, which is the red point. Let me zoom in. So if I zoom in, if you see there's a difference between the actual and the predicted. There was still a loss between the actual and the predicted value of that sensor. So we further did some processing. So we did some smoothing technique where we can reduce some noise and filter out some high frequency fluctuation. So we applied some exponential weighted smoothing. Next step we did is the differencing, where we eliminated all the daily fluctuation that happens or some seasonality patterns. And then finally, we normalize the data to ensure that there's a consistency in the data. So when we further enhance the processing of this data, the model gave a minimum loss, and you can see the green one is your actual test data, whereas the red one is the predicted test data, and there is very less difference between the actual and the predicted. And this black lines, dotted line, you see these are the anomalies that model has predicted in the test data. So that was the whole research of ALTEMIS. Finally, today is the World Listening Day, so thank you for listening, and thank you.